Okay.
All right. Welcome, everybody. So good to see you all, both with us live and those joining us after on YouTube. It's been a little while since we've been together. And as one of our attendees just mentioned, a couple things have happened since we've been together. I'm Rebecca Berman. I'm moderating this discussion with our wonderfully talented host, Glenn Grossman. As you know, Glenn Grossman is an epidemiologist with over 20 years of experience. While pursuing his doctorate in epidemiologist, let me say that again. While pursuing his doctorate in epidemiology at UNC Chapel Hill, Glenn served as an epidemiologist on staff at the UNC Infectious Disease Clinic for 2 years and taught epidemiology on staff and advanced analytics at Duke Medical School and at UNC. He has been involved in epidemiology projects with Medicare, Medicaid, Veterans Health Administration, Military Health Service, CDC, and other programs in the United States and outside of the United States. He currently is Senior Director of Outcomes Research and Epidemiology at Novartis, but all views expressed today are his own. So Glenn, I am looking at your beautifully welcoming fireplace and thinking, wow, this is now the third season. Should we call it seasons? I mean, I really think of these episodes should have chapters and seasons, and we're actually into the third season. I cannot believe it. Spring, summer, now fall, that we are together again. And while much has remained the same, certainly a lot has changed over those past 3 seasons and certainly over the past 2 weeks. So if you could kick us off today by taking us around the country and around the world, and then we're going to be jumping into some questions that came in from the audience about airplanes, and certainly many in our audience are very curious about our President Trump and the administration and what we can learn from your epidemiological perspective. So take it away.
All right. Sounds great. Thank you back, everyone, and in particular, Rebecca Berman. I appreciate it. It has been a couple of weeks, and a lot has happened since then. What I was planning to talk about today was not what I was planning about a week ago that we'd be discussing today, but a lot has happened in the world. So let me share my screen. All right, so like we do most weeks, why don't we just start big picture view. Where are we in the United States? What's going on with the world? Just to just see where we are, what's happened over the past few days. All right, so as we know, at a high level, the US had our first surge. The diagnosis rate was poor. That's why these numbers are small. Then we had the second surge, which is starting to drop. You remember that after the first surge, we sort of never got down to zero. We never got it under control. And so this was our new, in around early June, that was our new floor. And so then from there, we had the second surge that went from there. Now the second surge started going down. And then by end of September, that was our new floor. So now we've entered the third surge, the beginning of the third surge. And this has the potential to be at least as bad as the first surge. And we can get into that a little bit later. As you see on the hospitalization rates for the first surge and the second were around the same. I think that there were more people hospitalized in the second surge, but the length of stay at the hospitals was shorter. And so even though there were more people, because they were leaving the hospital sooner, the total at any one time, this currently hospitalized is the total at any one time. So that total was less, or was roughly the same in the first surge and the second surge, just because that dynamic had changed. Also, we had a bunch, and the reason for that was we had a bunch of better therapeutic options in the second surge than we did in the first surge. So just by pushing it out the 6 months or so, I guess 4 to 6 months, had a big impact in the fatality rate among those who were diagnosed. And now we're hoping with the additional therapeutics coming that the third surge that we have, we're hoping that it's not going to be as many deaths as we saw in the first surge. The key thing, something that we've discussed before, is that so there's a seasonality to respiratory viruses with cold and flu. The seasonality, it tends to be that it spikes from around October to, let's say, February, March. And so we've been eyeing the southern hemisphere with eager enthusiasm to see, hoping that it wouldn't spike down there. Because as you recall, in the northern hemisphere, when it's winter here, it's summer in the southern hemisphere and vice versa. And so we've just got out of our summer in the northern hemisphere, so they just left their winter. And based on this, we know that the southern hemisphere got hit really hard. The best estimate I have is that the SARS-CoV-2 became around 30% more contagious because of winter seasonality. And then in addition to becoming more contagious, there's likely to have been an increase in severity associated with that as well. For a variety of reasons, people tend to stay inside more, and so it's easier for people to spread the disease inside. The air changes. We know that higher humidity reduces the spread. We know that just being outside, even if you're in close proximity, UV light might have an impact. And so wintertime, it's just easier to spread for a variety of reasons. So the worry is we're already starting to see this. When you break it down by region in the United States, you'll notice that the Northeast got hit first in that first surge early on, and then we got it down pretty low, never to zero, but pretty low. And it's been slowly creeping up over the last month or so. In the rest of the other regions of the United States, the Midwest, it's been climbing faster. The South had been going down, but now it's kind of flattened at a high level. So this is their new floor going forward. And then in the West, it's also been going down. So we haven't before had all the regions in the United States going up simultaneously. The Northeast got hit really hard at first, but to a much lesser extent in other places around the country, particularly the West and whatnot. So because of that, in fact, let me share with you some interesting slides that I took. So one way of looking at the severity of the disease is the number of diagnosed cases per million. And when you look at the peaks in different regions and different states, you'll notice that the peaks were pretty high. So for instance, in New York, the peak was 595, give or take. I mean, that was one day. On average, the peak looks like it was still in the high 500s. New Jersey, the peak was in the high 400s. Massachusetts, there was this one outlier, which is probably just a data issue, but still mid 400s was the peak. Rhode Island around 400 was the peak. When you start looking at other parts of the country, Arizona had a peak of 670. California was in the low 300s. Idaho 400, Nevada mid to high 400s. I'll just go through a few more just so you can see. In Wisconsin, I'd say mid to high 400s. North Dakota was in the low 600s. Iowa, I'd say the peak was a little bit lower than 400, even though they had that one spike. Montana was low 300s. And then finally, I'll get into the South where they got hit pretty hard. So Florida, they had one day where it was 700 cases per million. Mostly it was a little bit above 600 was the peak there. Alabama, I would say closer to like 500, high 400s. Georgia, 400. Louisiana had a day of 826 per million, but mostly it was, let's say, around 700, it looks like, if you look at the peaks. Mississippi, 640. Oklahoma, 400. Some of these were less. Texas had a peak of less than 400, let's say high 300s. Washington, D.C. was high 300s essentially, and Tennessee was around 400 or so, maybe a little bit more. And so you can see the reason I'm calling these numbers out is that you're seeing when you look at this at a state level, the peaks are happening at different times. Here's Florida, mostly happening in July to early September or so. But when you compare that to New York, that hit way earlier in New Jersey. So even though the numbers were high, so here's Florida, the numbers we hit were let's say low 600s, and in New York it was almost 600, but high 500s and high 400s in New Jersey. These numbers are high, but the peaks occurred at different times. So when you look at the average for the United States, it appears much smaller. And so the reason that I'm pointing this out is when we look at global, and so let me share with you the global view. I am sharing. All right, so when we look at the global view here, you'll notice this is per million, which is a typical way to compare different countries. You'll notice that the United States doesn't look nearly as bad as a lot of these other countries. Even though we do look bad, I should be very clear. Our peak here is only 200 per million because of the way the peaks within the states all peaked at different places. So if instead of looking at the United States, so across Europe, what we're doing is we're looking at specific countries in Europe. But Europe has many countries, and all together, when you add them up, they're roughly the same size as the total population when you add up all the people in the United States. And so, in fact, our states are performing far, far inferior to other states. Like, so here's France. Relative to United States, it looks pretty bad in terms of where it is now. But based on what I just showed you, our peak was not 200 when you look at the state level. We had states that were hitting 700 or higher. And so that's one of these key reasons why a lot of epidemiologists are really critical about the United States and are saying don't be deceived by some of the data or some of the news you might be hearing. We are doing really poorly in the United States in dealing with this virus. And so I want to just show you this. So I like to take a look at different countries just at a glance in terms of how they're doing. Australia just got out of their winter, and it was really hard for them. They had their first peak when much of the rest of the world was doing it. Then they got it down to virtually zero. But even though they got it down to zero, in their wintertime, it was just really challenging to keep it under control. So even despite their best efforts, and they were doing a great job, they were doing enormous amount of diagnostic testing, far, far more, orders of magnitude more than the United States per positive case. And they still had a surge. But just even this surge was not anywhere near the quantities in much of the rest of the world, and they were able to get it down pretty quickly. South Africa had a surge. I'm not sure where they are right now, but they were also in their summer. Let's see, so they're still red. No, did I miss them? There's South Africa. So South Africa was doing really well at the beginning, but then they hit their winter. They got to roughly June or so, and then they had to shut down because there was no way to keep it under control. They shut down, and very quickly after they started getting it under control, the R value started coming down, and then finally they're near under control now. They were successful at bringing it way down very rapidly. They still have a little bit to go, but they were very successful. They're taking it seriously. And so when you look across the board, and now when you look at South America, for instance, Argentina is still going up. You can see it's just they've been having a terrible winter. That's the winter from hell in South America. And here's Argentina. And when you look at some of the bigger countries there, I mean, if you take a look at Brazil, Brazil was going up really high. They were having at their peak 50,000 cases a day, 60,000, 70,000. Then they started getting it down as winter started going down. Now, as you know, it's springtime in South America, so the normal seasonality of it is starting to go down, and in addition to that, Brazil is going down. Their testing is pretty poor, so it's hard to know how much of this is real versus just not diagnosing enough. But I believe that they are starting to come down just because it was out of control there for a while. Yeah, and so when you look, I mean, Chile went up for a while. Now they're going down. Their testing was also poor. Peru, I like to look at as in South America. Peru, their testing was poor also. They were going up, then they kept it at a high level, but then it went up again, and so they're still not out of the woods. But now, hopefully, as their spring continues and they enter summer, it's going to be much easier for them to get down back to zero. But so this comes back to us now. So here it is, the United States. We're entering our typical cold and flu season, and so now there's a lot of worry. Luckily, because there was so much precautions in South America and the Southern Hemisphere, in terms of wearing masks, in terms of not going out as much and having physical distance, the flu plummeted. There was virtually no flu in much of the Southern Hemisphere, which was astonishing. It's one of the lowest flu seasons on record in the history of tracking the flu. And so this is really astonishing. And yet, despite that, despite all of these, the masks and everything else that people were doing, you can see that COVID-19 was still spreading so much. So it's clearly an extremely contagious disease. A lot of people are dying from it. There's over 1 million people that have died from COVID-19 in the world already. And it's not going away anytime soon. So we'll talk about this a little bit more. This is where we are. It's just, it could have been dealt with a lot differently in the United States. There were countries, when you look across Europe and you compare how different countries are doing, clearly, like when you look at Germany, Germany is doing far, far better than the US. They treated it seriously. The virus is the same virus around the world. There's minor differences. We sometimes call this that there's genetic variants because there's slight differences, but there's not any major mutation that would make it a different strain, the way that we have different strains of flu that come each season. They're just minor variants. So it's essentially a clone across every single country in the world. And that means that the only things that are changing the course in different countries are how the countries are managing it. In addition, sometimes there's cultural things in addition to that, in terms of if it's more rural versus urban, in terms of in Asian countries, they have a history now of wearing masks more often because of some of the outbreaks that they've had over the last 10 years or so, or longer, 20 years. SARS, MERS, et cetera, have hit different countries differently. But Germany, they knew what to do. They followed the rules, and they did well. The United States, we knew exactly what to do, but we didn't follow the rules, and both our economy and COVID-19 are suffering as a result. There's a lot of pain, and it's that this is going to be a really tough winter in the Northern Hemisphere, but particularly in the United States. Yeah. All right. So having said that, let me jump in. So Beck, let me give it back to you. Oops.
Okay. So thank you, Glenn. Thank you for showing us in depth what's happening around our country and what's happening additionally around the world. So we're going to get into some questions from the audience that have come in over the last couple weeks. And if you have questions, please send them to me via the chat. Send them to me directly, and I will work to get your question into the queue. If we don't get it answered tonight, we will certainly have your question ready to go for next week. Okay, so Glenn, a question that came in earlier was about airplanes. We're very curious about airplanes, and do we know anything more about how easily the virus can spread on airplanes?
Yeah, so there have been some really interesting studies on airplanes that have come out recently. So it turns out that, yeah, there has been a fair amount of spread occurring on airplanes, despite their best efforts at circulating the air and trying to make it clear. There's clearly been a bunch of spread. So I'll just go through a few of the studies. But the first study here, there were 7 people who were ill with SARS-CoV-2. They found out after they were on the plane that they were infected at the time, and 2 people were likely to have been infected on the plane from these people who had not been diagnosed when they flew. When you look over here, here's a different study, but it's looking at specifically where people were sitting on a plane. It's a little bit hard to see because it's kind of small, but the red one is the index case. So this is the person who was sick. And then the orange ones are people on the plane who also got sick. And so you can see that in the first class or the business class seating area, it was essentially a super spreading event. And so all of these people all over, and in the first class, people are sitting a little bit further away than they are back in the in the in the regular in the coach class. And so despite that, you can see that that there was quite a lot of spread in the first class in this area. And additionally, there were some in the coach area as well. I mean, it could be that people got up to go to the bathroom or for other reasons, and that's where they caught it. So this is problematic for the airline industry. Um, a couple of other studies looking at this, and that one interesting thing is that it's been replicated on a bunch of airplanes now with a few different studies. This one was looking at a flight from Boston to Hong Kong, because the genetic sequences were different in the two different countries, then that gave them confidence that the person was infected on the plane by someone who picked up the virus in Boston rather than Hong Kong. And similarly, this is the last one. So looking at again, the index case is the one that's sick, and then seeing who they might have infected. They found that there were other people that were infected during the flight. And so yeah, I think that this is an ongoing concern. We don't have the planes under control. I'm not sure exactly when these were published in terms of, or when the data was all collected, because you see some of these, like this was February to March. So this was before there was widespread use of masks on the planes. And so now on the planes, there's much more widespread use of masks. And so as a result, you'd expect that the risk would go down some. But having said that, the risk is still going to be non-zero. So there's still going to be a risk, just because you can see when you have a super spreading event like this, even wearing masks, even if it helps, it's going to be challenged to eliminate the risk to a level that many people will find safe enough. The biggest thing is, so the time duration makes a big difference. And so for short flights, maybe if you're only on the plane for an hour or two, then the risk might be less than if it were a 6-hour or 10-hour flight that you're talking about. So, so these are things to consider.
Very helpful. Glenn, I'm looking at the, I guess that's a flight attendant all the way in the back. Is that what this is showing?
Yeah, I don't know if that was orange because she's orange or orange because it's just, you're right. It looks like the orange was
Maybe that person was working in the business first class.
yeah, probably. I forget. I haven't read this article in a little while.
No,
But
that's interesting. Or perhaps that's the way the air flows. I'm thinking about that. I often think about that diagram you showed us very early on about that restaurant and where the people were sitting vis-a-vis the air conditioning ducts.
yep.
So I'm wondering if that's similar here.
And it's one of these reasons that we're highly confident that the virus is aerosolized, that it's almost like a dust particle that just stays in the air and can travel very long distances. And so in that case, because it's not simply just small particles that just drop within 6 feet, the 6 feet rule doesn't apply to aerosols. And that's why you can have super spreading events like this where a lot of people in the area get infected, because the air can recirculate and just infect them. All right.
So now I'll be thinking about this diagram right along next to the restaurant diagram in my mind. Another question that came in was, do we know more about how the virus impacts the brain? You know, we often think of this virus as being a respiratory virus, but now we're hearing that so many different organ systems are affected. And what more do you know about how it impacts the brain?
Yeah, that's a really good question. So there have been a bunch of studies that have come out in the last month or two looking at the brain. So as we know, the ACE2 receptor, I don't know if I pulled up. No, I didn't pull down a list. So the ACE2 receptor is found all over the body in lots of different organ systems. So we know when it first started that it's widespread in the lungs. And so that's why it was originally considered a respiratory illness. In fact, SARS is severe acute respiratory syndrome. And so it was seen as a respiratory disease. It wasn't until later that we realized that it truly is also a heart disease and a brain disease and a kidney disease and a liver disease, and gastrointestinal system is implicated. It occurs, the ACE2 receptors occurs in much of the body. And everywhere that an ACE2 receptor occurs, it's being investigated in those organ systems or those systems, what if there's infection occurring and what the outcome of that is. I think that we've talked about heart previously. I'll talk about brain now. So yes, it's definitely a brain disease. The issue is that we didn't know about is, so we have the brain-blood barrier, and that makes it really hard for pathogens to cross. And so if a pathogen crosses the brain-blood barrier, then the challenge is that it's hard for our antibodies to cross. And so that means that it could be a real challenge to clear the brain if the brain is infected. And so that means that there could be more severe brain disease if there's no strong antibody response because of the blood-brain barrier. When we talk a little bit later about some of the topics that are coming up that we have to think about with Trump, how the virus spreads around the body becomes a really important question, and we still don't have a good answer on that yet. We do have some answers, but it's still a lot of uncertainty. So talking about the brain, here are the key symptoms that are somewhat common in COVID-19 that led us to know pretty early that there were neurologic things going on. For some of the symptoms that people had in various parts of the body, it was unclear if it was direct in terms of the infection directly infecting the organ, or whether it was indirect, where the immune system might have gone haywire, and then it was just a systemic immune system issue that was causing it. Here are the neurologic symptoms, and so I'll get into in just a second why we know that it's actually the brain being infected as opposed to just a systemic issue. The symptoms that we're looking at are psychosis, disorientation, confusion, delirium, memory loss, which could be significant for some people, dementia symptoms, stroke, encephalitis, and multiple sclerosis-like. The multiple sclerosis-like symptom was interesting because it was this symptom that was experienced by one of the patients who participated in the AstraZeneca clinical trial. And that's what stopped the clinical trial, because they didn't know if it was the vaccine that was causing it or if it was COVID-19 that was causing it. And so it's because it's a very, very rare thing to find, and they're still not sure. They restarted some of the trials in parts of the world, but I don't know if the US has restarted it yet in the US. I'm not sure yet. When it comes to the brain, I'll just jump to how we know what we know. There's three main lines of evidence at this point in terms of the studies that have been done to sort of conclusively demonstrate that brain is being infected or affected. And we don't know how widespread it is yet. So we don't know the prevalence rate of how much disease is occurring in brains among people who have COVID-19. But right now, the three lines of evidence are: one, the brain was in the lab, neurons were able to get infected. So we were able to prove that if the virus can get near to the neuron, then the neuron can get infected. So that's sort of like a proof of concept, but it's kind of weak because it's hard to know, okay, what does it actually happen in people? The second was to look at, over here, this was looking at mice. So among mice, they were able to give them the human ACE2 receptor. So they genetically modified the mice a little bit, gave them our human receptor in the mice, and then demonstrated that the mice were getting sick with the infection. They were easily infected with it. And so that is also strong evidence that the ACE2 receptor in a living organism can get someone sick. But the third and most compelling thing was that they went and looked at patients who died from COVID-19, and they did autopsies of the brains. and they found that there was infection, that there was SARS-CoV-2 in the brains with the autopsies of COVID-19. So we know conclusively that it is occurring in some people. We don't know how far widespread it is, and we don't know if it's what the long-term consequences are. One thing I like to come back to for a second is the similar question with the heart. So I think that we talked about this in previous weeks. There were two lines of evidence with the heart, in addition to the cellular stuff, which I'm not going to revisit right now. There was a study in Germany which was looking at 100 patients who recovered from COVID-19. So that is to say that they were part of a registry. So they tested positive for SARS-CoV-2. They were told to go home and to just stay home until they got better. The vast majority were asymptomatic or mild disease. Some had moderate, but they all stayed home. And then when they got negative test results, so they were assumed to have cleared the virus or whatnot, they went and had MRIs for these 100 patients. And astonishingly, 78% of them under the MRI, the magnetic resonance imaging, revealed cardiac involvement, cardiac illness. So inflammation and cardiac problems. 78% of these people with asymptomatic or mild disease, they didn't have, so the asymptomatic, another way of saying that is that they didn't have any symptoms. They wouldn't even know that they had SARS-CoV-2 if they hadn't been diagnosed with the diagnostic test. And yet, a lot of them are having heart disease as a result of that. In many of them, it had gone away, but yet there was ongoing myocardial inflammation in 60% of the patients. So again, let me repeat this. These are patients who tested negative. So they were positive, tested negative. They felt fine at that point. The symptoms had gone away. They felt fine. And yet there was clear evidence of infection ongoing. Because feeling fine means that the immune system is calibrated and it's come back to normal, no longer feeling the flu-like symptoms or anything like that. And so there's not some sort of crazy immune response that's causing this because they don't have the symptoms anymore. And yet there's ongoing infection in the heart in 60%. We don't know how long it lasts. We don't know, is this something that they need to worry about for years? We don't know if there's scarring that occurs. We just know that this is something that is deeply concerning that we have to pay attention to. Another study that was even more interesting than that was looking at college-age students who were athletes. So competitive athletes, these should have been the healthiest of the healthy. And so what they did was they looked at patients who had COVID-19. Either the majority were either, again, mild or asymptomatic. And they found that upon recovery, 15% of them had cardiac issues, had heart disease. 15%, which is huge in college athletes. Half of them were asymptomatic. So these were kids in college who had no symptoms, no idea. They had the test, and the test said that they were positive, so they knew they were positive, but then they cleared it, or they thought, and they got negative tests in their nose with the nasal swabs, and yet 15% when they investigated more closely. We don't do heart swabs in the United States. That's why it's so expensive to do MRIs. And that's why we can't do it at the population level. We have to do cheap, inexpensive tests that you can do millions of them. And so this is really, really worrisome that these kids who should have been the healthiest of the healthy, 15% of them had heart disease associated with it after they thought they cleared the virus. So it's disconcerting. So we know it's a heart disease. We know it's a brain disease. The evidence is quite clear. And so we can't be thinking about it as respiratory. Just because someone gets a negative test result after they've been positive, we're just swabbing the nose, the nasal area, sometimes the spit, but it's just this area up here. But clearly the disease is still ongoing. The infection is still ongoing in many, many, many people, but there's just no way for us to diagnose it because we don't have a swab test for the heart or the brain or the kidneys. So that's the answer to that question.
Goodness. Yikes. Well, better that we know now, right? And I appreciate that you're taking us not only around the world, but around our bodies so that we can really understand, in real time what this disease is and what we're learning. So I appreciate on behalf of all of us, you sharing this information as much as we don't want to hear it. We appreciate it. So let's move on now to the big conversation, the news of the week. And as everybody knows, we really do try very hard to keep this an apolitical conversation. So, we really want to, Glenn works really hard to share the facts as he sees them. So wanted to kind of point that out and begin the conversation that way. So Glenn, take us through what's going on with President Trump. Tell us what you know and what you think you can sort of deduce based on the facts that you're experiencing.
Yeah, and before I go on even get into the weeds, I need to say it's really important for Trump to get back on his feet and completely healthy within a day or two. And the reason is that, and I'll get into the details in just a minute, but the reason is he was given our best candidate for the best therapeutic options. And so basically, I'll go through the therapies and everything in just a second and what we know. But the key thing he was given within hours of the diagnosis was he was given a shot of pure antibodies. And our vaccine therapies, our all the therapeutics that we're planning on getting available in the coming months are all based on this premise of antibodies. And so Trump was given pure antibodies to stop it, to stop the disease process in its path. If this doesn't work, then that means that COVID-19 as an epidemic might continue on for not just a few months, but for years, because it means that the vaccines are unlikely to be effective. They might still be, but it makes them much, much less likely to be effective if the antibodies don't work. And so because of this, first of all, I'm very optimistic for Trump. I think that personally, I think there's under a 1% chance that he gets really severe disease and dies. It could, there is uncertainty definitely in what I'm saying, and I'll go through that in a second of why I believe what I believe. So clearly he is a really high risk person in terms of some of the things that he has. I'll get into that. But so just at a high level, the first reaction from a typical physician, this is Dr. Jeremy Faust. He's at Brigham and Women's Hospital in Boston. Boston got hit really hard. So he says, this is a nightmare. When we first learned about this disease, it was the patients who fit the president's description who we were most worried about. And so let's go on and see what's happened to Trump, what the timeline was, and what's going on with what's his risk, what's the therapeutic options that he's taking, and what's his prognosis. All right, so let's take a big step back. A lot of people suspect that the possible exposure was in the Rose Garden Supreme Court announcement that took place. That was Saturday, September 26th, so around a week ago, a little bit longer. And then on Tuesday, the presidential debate, the Tuesday of this past week was the presidential debate. Wednesday, and so if he was infected on Saturday, then he might have been contagious on Tuesday or Wednesday. Tuesday was the presidential debate. Wednesday, Trump attended a fundraiser and rally, and it was on Wednesday that Hope Hicks developed symptoms. On Thursday, Trump received the test result, the positive test result for SARS-CoV-2. This was Thursday night. For me, the big question is, when was the previous negative test? Because theoretically, I believe that Trump was getting tested every day, but that's not clear to me. I mean, did Trump just decide to skip a day? And so we don't know. Was he positive for multiple days if he had been tested, or was he only positive for 24 hours, let's say? That makes a big difference because it's an indicator of how much virus, what his viral load was in his body. And that hasn't been communicated as of when I put the slide together on Sunday afternoon. So that's a big unknown. When he was, so on Thursday night, he realized he was positive. Late Thursday night, early Friday morning, he made the announcement, the diagnosis. By Friday afternoon, he had already received the polyclonal antibodies that I'm talking about. I'll talk about in a little while. So this pure antibody injection. So that would have gotten to work immediately. And it's like a vacuum cleaner. This is what we're expecting, that the antibodies will go in and just suck up all the virus throughout the body and just clear it out. And so you'd expect that his symptoms would go away really rapidly and whatnot. A little after that, he was taken to Walter Reed Hospital. At Walter Reed Hospital, on Saturday morning, he started a 5-day course of remdesivir, which exists now under the emergency use authorization. Polyclonal antibodies are available under compassionate use. So drug manufacturers are able to give a portion of their drug away under this compassionate use, but it's a very, very small numbers with very specific criteria of who gets it and when. And then also on Saturday, Trump was given dexamethasone. So let me go through just a few things, and then we can get started, dig in a little bit more. All right. So typically, where you are in the disease progression determines what kind of drug you get. So at the very beginning, during the incubation period, you first start having viral replication because there's no immune system response. There's nothing to control it. There's no breaks. So at first, it's very, very large, and then you start getting symptoms as the immune system starts to respond to it. And so then the viral response gets lower and lower over time, and it shifts from being primarily a viral disease to then, in many of the cases that get really severe, to becoming really immune system cytokine storm, where the immune system just goes crazy. And so there are issues where a lot of people, even if they avoid the immune system going crazy, they're still dying because of blood clots, because of heart failure, because of what we said, the brain diseases. So we're seeing a lot of people who are dying. On their death certificates, it says dementia, but that's way more people are dying of dementia than they did last year or the year before, or the year before. It's just a lot more. So something has to explain what's going on with dementia. It could be that people in nursing homes or long-term care facilities, if they're not getting as much social stimulation, then they might, that also could contribute a little bit more towards people declining a little bit faster. But the fact that we're finding SARS-CoV-2 virus in people's brains means that it's on the causal pathway. And so we haven't been able to tease out what's responsible for it yet, but I'm confident some of it is related to the virus causing the brain disease. Anyway, so where is Trump? Trump is early on in the viral response, because within a day or two of him having sufficient viral load to trigger a positive test, he was already identified, because he was giving tests so frequently. That's what it should be for the rest of the population. It should be the case that most Americans are getting tested at least once a week, and we're not anywhere near that. And especially people who get tested, for most of us, it might take a week or longer before we even get the results, which is crazy, because then you can't do anything with it. If you got the result within the day, then at least you could shelter in place. You wouldn't have to worry about infecting anyone else. You could contact trace, and anyone who you might have gotten infected from, you could go and tell them, and then see who they might have also infected. If that was the way it was supposed to work, but we just didn't process it that way. There was a limitation in the number of tests, but we knew you could do batch processing, and we're still not doing a ton of batch processing. But batch processing is, instead of doing one test where you have one swab from one person and then test it in the PCR, instead what they do is you might take 10 swabs, take half the samples from each of the patients, and batch them together and into a group of 10. And so then when you have a group of 10, if everyone's negative, then you'll get a negative test. And you'll only have had to run the test once, and then you'll have, instead of running it 10 times, by only running it once and getting the negative result, then you eliminate all of those other tests that you could have done in order to get the negatives. And so then if you do this a lot, even if one person is positive, then you go back and retest the other 9 that were, or each of the 10 that are in there, to see which were positive and which were negative. And it turns out when you do this batch processing, it's really effective. We should be doing it right now. It's a way to dramatically speed up, especially if we're getting positive infection rates of like 3% or 5% on average across the country. Then that means that you could batch 20 people together, 30 people together, and most of them would end up negative. So you'd be saving all of this time by avoiding processing all that. Anyway, I'm diverging a little bit from the main topic here. Let's go back to Trump. Here's Trump. Trump is very early on. He was usually remdesivir is not given until people have more severe symptoms. So typically, it's not until you get more severe symptoms where people are given remdesivir. It's not really given when you first get a positive test. Similarly, corticosteroids, so dexamethasone, is not typically given until all the virus is done replicating, until you already start having antibody response, because the problem with corticosteroids is that they lower the immune response. And you don't want to lower the response over here. You do want a stronger immune response at the beginning because you want to build up antibodies. But most likely what the physicians are thinking are that because Trump has been given pure antibodies, that it's okay for them to give the dexamethasone because the antibodies will be sufficient, is what they're thinking. All right, so this is where we are. This is what the course of the disease looks like for most people. Let's go a little bit more in detail. All right, I think we've seen this slide before. This is just the different timelines that you expect from different components of the immune system. And so there's a lot, it's complicated. There's a lot of going on in the immune system. The B cells with the antibodies, there's T cell involvement, there's immunoglobulins, these antibodies that are formed. Yeah, so lots going on. And you can see that over the course of the disease, which ultimately the different levels decrease, and immunoglobulin G ends up being the longer term antibody for protection. Goes down to a low number, so even if it's not detected in antibody tests, that's not a bad thing because it is still there. It's just at undetectable levels for lots of people. And then theoretically, if they're reinfected, it would provide protective immunity. That's how for many diseases it works. All right, let me skip next. This was the Rose Garden Supreme Court announcement at the White House. And so even though it was outdoors, they did spend some time indoors. You can see virtually no one was wearing the mask. There were one or two wearing a mask, but virtually no one was wearing a mask at this event. There was no physical distancing. This is the President of the United States in the middle of an epidemic. He was trying to make a case that, oh, the epidemic is over thanks to the work that he has done. But it turns out that that was not the case. There were at least 8 people who attended the ceremony who have now tested positive for SARS-CoV-2. So this could have easily been the place where President Trump, Melania, and them were infected. Next, so in terms of looking at the administration, a lot of people have started to become infected over the last few days. And so there were some people were not in contact, but you can see that it's spreading. One thing that I wanted to do, let me see if I can find it real quickly, is the probability of testing positive if you are infected. Let me see if I can find it really quickly. We've accumulated so many slides over the last
It's
month.
impressive, Glenn. I'm looking at this deck you have here.
A
And
lot.
it's indicative of our past 6 months together. And I wish you luck finding this slide. But don't fret. If you're unable to find it on the fly.
We'll talk about it next week. Oh, here it is. Here it is.
Well done.
So what I like about this slide is that this tells you if you are infected at time 0, how many days have to go by before you're likely to get a positive test. So this one is the probability that you are negative given a positive test. And this one is probability that you're infected given a negative test. And so these tell you slightly different things. So the first one is, okay, these people are getting negative tests, what's the likelihood that they are infected, truly infected? So at day one, they're getting a negative test, but there's still over a 10% chance that they were actually infected. But then as it goes on from this index date, by around day 5, they get very near the lowest point. And so by around day 5, day 6, it's under 5% chance that they are infected. This was done based on a assumption of how widespread the infection rate, what the prevalence rate was at the time. So it's not going to actually be the same total magnitude. It's mostly the shape of the curve that I want to pay attention to here, because we don't know what the underlying risk was in the area in which these people got infected. But this one is more interesting. So this is the probability of the test being negative if the people were truly positive. So that means they may actually have COVID or SARS-CoV-2 infection, but they're getting negative results. So it's roughly 100% chance that they'll get a negative test result, even though they were infected, because they're only incubating at day 1. At day 2, still 100%. At day 3, there's a slight chance. At day 4, there's a much bigger chance that they'll have a positive test result. At day 5, they get close to the maximum. Day 5, day 6, it's much less likely to have a false negative result at that point. So by day 5 or day 6 after exposure, that's an optimal time to get a test if someone is exposed. And so if Trump tested positive, then it was probably around day 5, day 6 or so. And the fact, what's totally surprising to me is the fact that they had symptoms on roughly the same day that they had a positive test result. Because normally symptoms don't happen until days after you could get a positive test result here. And so, I mean, some people do start getting symptoms on day 5 or so. So, I mean, it's not so absurd, but it's still a little bit weird because I was expecting that Trump would be tested daily. He had a higher chance of being tested on the 4th day or so, the 3rd or 4th day, let's say the 4th day. But it wasn't until he started getting symptoms that he also got the test. So I don't know, it's a little bit strange. But let me go back now to talking about Trump. It's so easy to get on these tangents because there's so many interesting things to talk about. All right, so let's jump into Trump's risk factors and symptoms. So Trump's risk factors, there's essentially 4, I think, or 5. The first one that I'll say, the risk factor is that he's symptomatic. So simply being symptomatic increases his risk of having severe symptoms and severe disease at one point. Because if you're asymptomatic, you're much less likely to have severe disease. A lot of people, or everyone who is symptomatic, was asymptomatic at one point, but some people who are asymptomatic remain asymptomatic. And so the asymptomatic people are in better shape. Obviously, we talked about there's underlying disease, their hearts can get infected and whatnot, but still they're in better shape than ones who get symptoms. So the fact that he has symptoms so far, and for most patients, they're mild at first, the fact that he has symptoms is a risk factor now. In addition, the other risk factors that are considered the typical ones are that his age is over the age of 70, he's 74 years old, he's male, he's obese, and he has mild heart disease. And so these things together put him at extraordinarily high risk. When you look at the risk factors, before I go on, let me talk about the symptoms. So here are the symptoms he's reported: a low-grade fever, fatigue, nasal congestion, and cough. So these symptoms, to me, all are typical of just an immune response. I don't see these things as anything specific to the ACE2 receptor. I don't see any indication here of trouble breathing, although it was reported, very hard to interpret, but it was reported that his oxygen levels may have gone down to levels where he was supplemented with oxygen. That's not clear, but that would have been another symptom. Right now, these are the commonly reported ones. And so it's really, there's not much transparency in what's going on here, which, I mean, from my perspective, I don't know that we need as much transparency. I can see the argument that he's the president of the United States. He has the nuclear suitcase. There's a lot that he's responsible for, And so if his health is at risk, citizenry should know. But in the same token, if something were to go wrong, we have a whole hierarchy, a chain of command, where the vice president could jump in and do whatever. And whatever our feelings are of the president or vice president, because we have this chain of command, for me, it sort of takes away some of the legitimacy of us really asking for what his disease, what his personal health status is. I think that it's relevant for two reasons. Other than that, one is he's had very specific directives when it comes to COVID-19, and most epidemiologists would claim that it was very poorly managed in the United States. And so because of that, we're interested in knowing what his disease progression is and how that may impact the treatment of the disease in the United States going forward. If President Trump were to suddenly have a eureka moment because of this experience and decide that he needs to be more aggressive in treating COVID-19 in the United States or managing it from a public health perspective, that would be amazing for us, because already over 200,000 people have died from COVID-19. My estimate is that it's almost 300,000 people that have died when you look at all the excess death that has occurred over the last 6 months. And that's a lot. And we're about to hit a winter of hell based on what you saw in the Southern Hemisphere that I just showed you a little earlier. And if Trump has a change of heart right now, then the next few months, regardless of who's elected and starts office in middle of January, we're going to be having winter months in November, December, January, that we need to have much, much better control over the public health, how we treat this as a public health epidemic in the country than the way we treated it over the last 6-7 months. And so this could be really positive for the United States in terms of if there's a change in course of the management. I see this as different than, say, the tax, releasing the tax documentation, because for that point of view, we want to know if there's any worry about any foreign manipulation or who is our loans owed to. It's a different type of question, because that's more in terms of understanding that there's no malfeasance or anything in terms of anything that's going on there. For this, in the United States and in much of the world, personal health information is really important that it stays private. And so I can see the argument for keeping many things private. He's the president of the United States during an epidemic, though, so there is a clear issue for transparency as well. But let me talk about the risk factors. So based on his risk factors, based on the risk factors alone, COVID-19 patients who are diagnosed with SARS-CoV-2, so not the asymptomatic ones, but patients who are diagnosed with SARS-CoV-2 at his age, if he's male, etc., they have a 65% chance of being hospitalized. So that's quite high. And among people with the risk factors, they have a 32% chance of dying. So that's also quite high. His personal doctor, in case you don't know, is Sean Conley. Here's a picture of Sean Conley. He's been a emergency doctor for the U.S. Navy. And so he's very competent. And so giving Trump the best treatment available in the world, I am certain. Here is his complicated treatment regimen. Let's go into this. I see we're already at the hour. I'll just go into some of these and then we'll call it a day. Maybe another 15 minutes or so. So these are Trump's therapeutics regimen. I'm going to go through just what the sum of evidence are for each of these. So the very first thing I mentioned are these polyclonal antibodies. We previously called them monoclonal antibodies. So that's when you take the most potent antibody. And so in this case, what they've done is a lot of people, many millions of people, my best estimate is maybe 50 million people in the United States alone have been infected with SARS-CoV-2 already. So they've screened the blood of people around the world to identify the very most potent antibodies. From this, they selected the single most potent antibody that they thought would be the most effective, and that's what they recruited to make clones of that antibody. In addition, they went the other way, and they looked at the virus itself, and they predicted what they thought would be the strongest antibody just based on the structure of the virus alone. And so then they created a second antibody for that. And the antibodies are slightly different, affecting slightly different parts of the virus. But they're doing two antibodies just in case, and let me show you, we've talked about this previously, but let me just jump to here. So antibodies are like, kind of like this cartoon. So this cartoon is you have different scientists looking at different parts of this elephant. And if someone looks very, very closely at the top, they might say, oh, look, it's a fan. And this person over here looking very, very closely will say, oh, look, this sticking out is a spear. And this person down here will say, look, it's a snake. And so each person looking at a different part of the elephant fails to see that the whole large thing is actually an elephant. They all are looking at the very specific thing. And that's the way antibodies work. Antibodies don't look at the whole big picture, they just look at the little picture. And so that means for the same virus, you're going to have lots of possible antibodies that could come about. Some antibodies will focus on this part, some antibodies on this part, some antibodies on this part. And different antibodies will be more or less effective. So they screened many, many antibodies from people. They found the antibody that they found in the population was the single most effective. They took that one, and then they did from their computer modeling what they thought would be the most effective, just hypothetically, and that they didn't find in humans, and then they took that one. So those two, and they just made massive number of clones of these. And so that's what is the monoclonal or polyclonal. Monoclonal is when you do one, polyclonal is when you do more than one. So this is the name of the drug right now. It's in phase 3 clinical trials, is REGN-COV2. And so we'll get into that. I'll just go through the list and then go through a little bit more detail about them and what we know. Remdesivir, you've heard before. He was given that within 24 hours or so, as far as I can tell. Maybe a little bit longer than 24 hours of his diagnosis. Dexamethasone, the corticosteroid, given that. Statins he's on. Don't know what the dose is. Vitamin D, zinc, melatonin. It's frequently used as a sleep aid. Famotidine is typically used as an antacid, and he's on daily aspirin because he's high risk for heart attack or stroke. And so let's jump into each of these in turn, because a lot of people, if this is the president of the United States, who's presumably getting the best treatment, the best care in the world, a lot of people will want to know, well, if we get sick, maybe we'd want to take these too. So I think a lot of people will be interested in, like, what's the sum of evidence for each of these? Why is he taking them? So let's just jump in. So what do we know about REGN-COV2? So Regeneron is the company that makes it. I actually, for full transparency, I worked with Regeneron previously on some monoclonal antibodies for cardiovascular disease when I was at Sanofi, prior to where I currently work. It's a great company. They know their stuff. My point here is that they have deep experience developing these clones of antibodies. They know their stuff. Two, it's called polyclonal antibodies because there's two different monoclonal antibodies. Great, I just said that. So here's the big takeaway that I need to reiterate. If pure antibodies don't work, then it may mean that no vaccine will work as they're currently conceived. And that means that this is literally what many epidemiologists are thinking is the top candidate in the therapeutic pipeline of all the drugs in the clinical trials. So we are all hoping that this works. So what's next? So Regeneron's cocktail, like I said, contains the human-made antibody, and then the other one that they designed, and they put them together. So far, it's only been tested on not a lot of people, on 275 non-hospitalized people. So this is for mild disease. And then they saw huge improvements. So both very quickly, the viral loads went down in these people and the symptoms went down. But so we still have a lot to see. All right, I went through this. I'll just briefly say some monoclonal antibodies have been used in a lot of disease areas at this point. In terms of the number of products approved, you can see that there's one for allergy, I think maybe even more at this point, dupilumab. I don't know if it was launched by I think it was launched by 2015. Autoimmune, 21 in autoimmune, 20 for cancer. Cardiovascular has been approved now. Immunologic, infectious disease. So there's a lot of indications. So we have, in terms of this mechanism of action, we have a lot of experience using these antibodies. So we know how safe they tend to be, and they tend to be extremely safe. It's pure antibodies. So therefore, there's not a lot of worry from this perspective. A vaccine is different because what a vaccine does is it changes your body so that your body actually produces the antibodies. And the fear is that in addition to producing the antibodies, you might be changing your body in other ways. And that might have long-term consequences because you get an antibody that's from a vaccine. And the hope is that you're protected from with this antibody for months or perhaps years. So there could be a really long-term impact on what the body is doing. In contrast with these clone antibodies, you're just putting pure antibodies in, and within a week or two, they will have just been eliminated from the body. So you're not doing any long-term issues to the body. So presumably, these monoclonal antibodies should be much safer than many vaccines might be. And so I'm less worried about the clones of the antibodies than the vaccines because of this reason. So I've mentioned some of the disease areas that they're in. Here's some others, just more specifics if you're interested. They've been out for quite some time. You see some of the earlier ones were even back in the late 80s. So there's a lot of experience working with these things. Now I'm going to jump to remdesivir. Remdesivir is so first the clones, these antibodies, that's an injection. That's something you can easily do. Go to the pharmacy, get a prescription filled, and just do it at home, or they can do it for you at the pharmacy or whatever. Doctor can give it. It's very easy to get once it's approved. In contrast, and most of these will probably be self-injection, I'm assuming. I don't know. In contrast, remdesivir is an infusion. So this requires an IV essentially, in terms of you have to be in a hospital or in a clinic where it's given. It's given over a 30-minute to 2-hour period. This is not something that's self-administered. I see we're running late on time. I'm just going to go through a bunch of these, not too much longer. So remdesivir is much harder to take as a result, and so it's much and so for most people this is not going to stop the epidemic because people are still going to be hospitalized. Something like the antibody clones could stop the epidemic if sufficient amount was made. Right now, the manufacturing would be a constraint, but if sufficient amount was made, then it could be evaluated for prophylactic use. It could be evaluated so that if anyone got a test, that day they would get a prescription and be flooded with antibodies. So this could theoretically, if it works, end the epidemic. All right, the next thing is, so remdesivir, this right now it's approved under, again, this emergency use authorization that we've talked about. Among 65-year-olds, it's 30% more effective at reducing their length of stay at in the hospital. And so reducing their symptoms, reducing their length of stay, remdesivir is great. The mechanism of action is still unclear, but it's been demonstrated through some of these early clinical trials. It seems to work. There's ongoing clinical trials, and then it'll see if it'll actually continue to be as safe and effective as we think that it is. And because this is a different mechanism of action, that's an interesting thing. So now Trump has been given antibodies, and he's also been given remdesivir, and you see remdesivir act within the cell to prevent viral replication, whereas the antibodies act outside of the cell, hitting the virus itself in the bloodstream and outside of the cell. All right, next, dexamethasone. This is the corticosteroid we've talked about before. I'm not going to talk about it much more. This is almost always given only to the sickest of the sick patients or people who are who've already started to have a serious immune sequelae. The first, as you see, that among people on ventilators, it was the most effective, and among people on oxygen, it reduced mortality by 20%. There was no effect found for people who are not on oxygen. So this is not something that's given for people who don't require supplemental oxygen. One of the things that we realized pretty early on is that we should be avoiding ventilators. That part of the problem with SARS-CoV-2 is that it structurally damages the lungs. And part of the process of breathing deeply to try to get enough oxygen further makes the lungs have structural issues where it starts to break down. And one of the things that they found is that if you start just supplementing with oxygen alone earlier on, then people don't have to breathe as deeply. And so it seems like there's less structural damage that might be happening. So that's one of the reasons that Trump was almost certainly put on oxygen. even if he didn't necessarily need it, just to prevent structural damage that occurs because there's insufficient oxygen that's going through, even if it's not a lot of insufficient oxygen. All right, the next thing is corticosteroids. So again, it's not typically given earlier. Probably the reason that they gave it to Trump was because his body has been flooded with the best possible antibodies that were identified in humans so far for curing the disease. The next thing is vitamin D. So you might be asking, vitamin D, so Trump is taking it. Is this something that we should be taking? And so the short answer is that there's right now have not been major clinical trials evaluating it. What there have been, so vitamin D, here's the story about vitamin D. Vitamin D deficiency has been found in a huge percentage of the population. Lots and lots and lots of us are deficient in vitamin D. In addition, there's a strong, an extremely strong correlation between being vitamin D deficient and having all sorts of bad diseases, cancer and cardiovascular disease, all sorts of different diseases. I forget the exact ones, but many, many, many different diseases have a strong correlation with low vitamin D levels and the disease. And so a lot of people thought, well, maybe we should be supplementing vitamin D, because if low vitamin D is associated with all these diseases, then maybe if we supplement with higher vitamin D, then we prevent all these diseases or cure the diseases. So there have been some major clinical trials that were conducted before COVID-19, and what they found was that vitamin D does not cure almost all diseases. There's a couple things, like, so for instance, vitamin D helps with the absorption of calcium. So perhaps people who have osteoporosis might take vitamin D if they're prescribed from the physician, because it could help them to maintain the calcium that they need so they don't have broken bones or whatnot. So there's a case to be made there. A problem is, because vitamin D aids in the absorption of calcium, that very reason is actually a bad reason for the majority of people who are age 65 and over who might be thinking of taking this, who might have cardiovascular disease. And the reason is, one kind of cardiovascular disease, if people have plaque in their arteries, is that they could get hardening of the arteries. And this hardening of the arteries is when calcium builds up in the plaques in the cardiovascular system. And so if you take vitamin D supplements, then you actually increase the amount of calcium going into your body. And then the fear is that you could cause, that it's unsafe. You could cause a lot of damage, because then you might have permanent hardening of the arteries because of taking vitamin D. And so this is an issue. And so for most people, we would recommend do not take vitamin D, because the supplementation has not been proven to actually do much for the majority of people. And so the question is, for COVID-19, should we? And so there have been some studies published that suggest, this one was in Iran in particular, I think the one I'm looking at here, which suggests that there's a strong correlation where people who are deficient in vitamin D are doing poorer with COVID-19. And so you would think, oh, see, this is another reason why we should increase our vitamin D, because presumably that would make them better. But there haven't been any clinical trials that are high quality, that are large, that have looked at this. There have been some small ones that have identified maybe an effect, but the sample size is so small, it's not enough for an epidemic to suggest that we should be doing this, particularly pardon me, particularly because we know that it could cause damage. All right. All right, I'm gonna wrap up in just a second. Excuse me. All right, the next thing, Pepsid-AC. What is this? Famotidine. So there were some early, one other thing about vitamin D is that there was some early reasoning of why it should work from a physiologic perspective. There are some theories of why vitamin D is protective for respiratory illness. The problem is that when you look at clinical trials, there have been some big clinical pooled analysis, some meta-analyses of these clinical trials, and they've shown no effectiveness of vitamin D at preventing or curing respiratory illness at all. And so because those are the generalized reasons why we think vitamin D would be helpful for COVID-19. It's unlikely it would be helpful for COVID-19 for those exact reasons. All right, Pepsid AC, I'm going to end it soon. There's just a couple more slides, just a few more I want to get through. So this is the same type of thing, a little bit different. There is better evidence, actually, no, it's not, I should take that back. There is somewhat better evidence for famotidine as actually being effective. Early on, there seemed like there was a signal that it could be effective, and so a lot of us have been curious about it. However, the quality is pretty low quality evidence right now. So despite that, there is some really interesting evidence that there could be something going on. And so we definitely need better randomized clinical trials to be evaluating this. It's not really known right now. It's not enough to really recommend prescribing it at the population level because there are risks for taking a drug like this. But there could be something there that's more that might be stronger than vitamin D or these other things. But let's go on. So Pepsid AC is something. I can talk about this in a little bit more detail when we have more time in later weeks. Trump is also taking melatonin. Again, there are some possible reasons and hypotheses why it could be helpful, just like vitamin D, but there's not any randomized clinical trials that have been completed that suggest that there's strong evidence. And so there are some clinical trials being conducted, but nothing that is really, this is an example, I believe, of Trump taking an over-the-counter drug because he thinks he knows better and he's doing it, and it's not, he's getting, sometimes melatonin can help people sleep, and getting enough sleep is important, but otherwise, I don't think so. Statin treatment. This is really interesting, and so I just wanted to get to this one. Statin treatment has been found to be protective against COVID-19. Let me say this again. So there have been a lot of studies, not a lot, but multiple studies now at this point, looking at statins and COVID-19. And you see here that it reduces the risk of COVID-19 severe symptoms by maybe 30%. We've seen in previous weeks that this line is no effect. So if it's on this side, then it's protective. If it's this side, it's worse. You see that in these multiple studies that have been published so far, it's a pretty strong effect, reliable protective effect in most of them. Some have not been as strong. In particular, when you look at this and you look at people with different risk factors, the risk factors are consistently increase people's risk of having severe illness from COVID-19. But when you look, pardon me, when you look at statins, statins have a dramatic protective effect, really protective. So if you're at risk with high cholesterol and you should be on a statin, but you're not, you should seriously consider going on a statin at this point. All right. One final thing, and then we'll leave it to next week. So this is a potential reason why antibodies would not be effective. There is something called, so this is the classical way we think of viral replication. The first is that a virus infects a cell, it replicates in the cell. Then when there's a lot of virus that are produced, it bursts open the cell and the virus goes around the bloodstream and infects the rest of the body. And so the classical way of thinking about this is that the antibodies then go and attack the viruses. The problem is, this is something unique. We've seen it in some other viruses, in particular SARS and MERS. But one thing that SARS-CoV-2 does that's really distinct from most viruses that we've seen is it reprograms the cell. So instead of making the cell burst open and then putting all the virus out into the bloodstream, it reprograms the cell and makes these long bridges that connect from one cell to other cells nearby. So it doesn't have to break open the cell. It can connect and travel. These green things are just to make it easier to visualize, SARS-CoV-2 virus walking along, not actually walking, they don't have legs, but they're moving along this bridge without going into the bloodstream. So as a result, it makes it less likely for the antibodies to be able to connect to them because they're not just flying away, they're on the cell and they're just migrating from cell to cell on these things. These protrusions are called phylopodial protrusions. They're phylopodia together. And so they occur, I'll show you some more pictures. You see that they're, the key thing that has been found now repeatedly in multiple labs is that with SARS-CoV-2, there are numerous protrusions that are found, so way more than would typically be found, and they tend to be longer. So I'm just going to go through a couple slides. So they are literally reprogramming the cell. And so you can see there's structural changes. And so when you look at this picture, for instance, you see like, oh, it looks like hair almost across the cell. This is not the way that cells typically look. And so these long protrusions can be a way that the virus spreads around the body where the antibody can't easily get to it. And that's the point here. So there are hypotheses of why the antibody treatment won't work. And in that case, why vaccines won't work. And this is one of the leading hypotheses. And so a lot of people are looking very closely at this. Luckily, the people who are looking closely at this have realized, oh shoot, I didn't put it here. I put it up here. So we're starting to understand the mechanism of action of what's going on here. And it turns out, so it's this molecule CK2 that's responsible for the pathway of the phylopodial protrusions occurring. And we found that there's a bunch of drugs that are being investigated for cancer that specifically prevent CK2. So it could turn out that the antibodies are highly effective, but not totally effective, but maybe we need one final drug combination and we need to increase the cocktail of drugs that are given to prevent this other mechanism. And maybe others will be identified, but then we'll add additional cocktails there. So I'm still highly, highly optimistic that, that Trump will be purely cured, but there still might be other reasons why the antibodies might not be sufficient. So I will end it there. I apologize it took so much time tonight.
You did amazing. And as you said about the pharmaceutical company for which you worked previously, they know their stuff. I think it's very safe to say that we can take that same line and say about you, wow, do you know your stuff? And how fortunate we are that you are our tour guide. And I know we did have a bunch of questions come in. So anybody who sent me questions during the program, I will get those to Glenn. And we'll do a recap of this kitchen sink, shall we call it, that has been thrown at President Trump. And perhaps over this next week, we'll learn more. And maybe you could take us through, the different elements once more, what else, that you're learning. And I will get those questions over to Glenn so we can start there with that piece of the Q&A. But wow, did you break this down for us and tell us what's possible, what's probable, and really so helpful. So with that, I will leave it. I hope everybody is safe, well, wear your masks, encourage other people to wear their masks, because it certainly sounds like for the foreseeable future, the masks are critical, right?
Absolutely.
You all are very best. And Glenn, thank you again for all of your hard work. We really, really, truly, truly appreciate what you're doing for us.
Thank you very much. And thanks everyone who's coming on the call every week. I really appreciate it. Becky in particular, but everyone, I do it for all of you. And because I perceive that you're getting value, that's what makes me interested in helping this and doing it for all of you. So thank you very much for giving me this opportunity.
Thank you. Have a good week, everybody.
All right.
Bye-bye.